Okay, I guess we have a good critical mass. So welcome to this Institute Colloquium, which is actually multi-purpose in a way. We want to commemorate the Bose statistics, which is little more than 100 years old. It was supposed to be 2024, but due to the cyclone, the speaker could not show up last in November. This is also a year of International Year of Quantum Science and Technology. And we have Quantum Center here, which is called the QIXT, that's Quantum Information Science and Technology Center, as well as QMET, which is Quantum Metrology. So we are going to have a bunch of events to commemorate the International Year. So with that, I would like to welcome Professor Baskaran from various affiliations he has. He's our speaker today. The title of the talk is Boson Bloom. So I'd like to introduce the speaker briefly. So by the way, my name is also Baskaran. The common joke is that I have an H, he does not. So this Planck constant joke here. Okay. So Professor Ganapathy Baskaran is an Indian theoretical physicist known for his work in condensed matter physics and strongly correlated quantum materials. Since 2012, he is a distinguished visiting research chair at the Perimeter Institute at the University of Waterloo, Canada. He is a distinguished professor at IIT Madras since 2019. He is an emeritus at the Institute of Mathematical Sciences in Chennai. So it's a long story, but the most important thing is he worked with Professor Anderson as a postdoc at some point, and he has a very famous theory with Anderson which is called the resonating valence band theory in superconductivity. And in connection with this, I did a solid state physics course under Professor Gabriel Giuliani long back as a grad student. And every time I was not paying attention, he used to throw at me and say, "You are Baskaran, you should know this answer." So, referring to, of course, Professor Baskaran. Okay, so with this not so short introduction, I will ask Professor Baskaran to speak, but I'll just quickly tell you a few of his achievements. He received the Distinguished Alum Award of IISc in 2008. He's also, among all the lists of awards, he's also a Shanti Swarup Bhatnagar awardee in physical sciences, and he was also the first recipient of the ICTP prize from the International Center for Theoretical Physics. Okay, so with this, and was also the member of the Institute of Advanced Study in Princeton. Okay, so with this not so short introduction, let me welcome Professor G. Baskaran and his talk in here. Thank you.
So thank you once again for inviting me to this wonderful place. Very happy to be here. And as Baskaran said that this year marks two important events. One is the birth centenary of quantum mechanics, as Lars Schrödinger and others. And also in 1924 is the year in which S.N. Bose wrote a famous Bose statistics article to communication to Einstein, and Einstein did this Bose-Einstein condensation work. So it's a confluence of two important things. So the director of S.N. Bose Center, my friend Tanushree Saga Dasgupta, she commissioned me to write an article about Bose because she knew my interest in some of these things. So I wrote an article with Alex May, who is from UK, on Boson Bloom. So that's the story I will tell today. It will be a very light story. I will show pictures and tell stories and so on. So please don't take this thing seriously. And that's what I plan to do today. Okay. So after a long introduction, I'll talk about quantum physics and blooming of international cooperation. How Bose-Einstein bond has made a big difference to science in general. And bosons are, family of particles. We'll discuss that. It has started with photon, and now we have gauge boson, Higgs boson, Hawking radiation, graviton, phonon, and many in solid state also. There are people working on it in IIT Madras, IIT Mumbai, Bose-Einstein condensation, superfluidity, superconductivity, and so on. So this is what I am going to talk about. At the end, I will tell some anecdotes about Bose as a wonderful human being. So I am originally from the Institute of Mathematical Sciences. It's a very small campus. I do not know how many of you visited that place. It's a green, just 10-acre campus as opposed to 500 acres here. Small campus. but greenery. This is a picture, all these pictures I took. You can see the bird occasionally coming during these are called, I don't know the name of the flower. In Tamil, I know the name. So these are hut we made for during Hubbard Model Conference. It has become a very permanent thing. And this is IIT Madras, where I am strongly associated now. You can see deers passing by. Unfortunately, we don't have leopards. I hear leopards do come here. 100 years ago, there were tigers, because there are evidences for that. And if you walk about 30 miles south of Chennai, there is a tiger cave on the way to Mahabalipuram. So when all the forests were connected by percolation, the tigers used to wander in that area. Now there are no more tigers, but you see monkeys and this black buck and these beautiful trees. And there is some controversy about this. Monkeys, students call it as professors, and professors call it as students. So, okay. And this is where I spend half of my time at Perimeter Institute of Theoretical Physics. It's a great place. I will tell about the origin of it a little later. Beautiful place. There is a lake, and then there is a small campus, and there is a zoo, little zoo beyond. It's a big green park, and it's a wonderful place. And this is IIT Bombay. When I landed, I was put in this. I'm staying in this Prema Vihar, very Padma Vihar. Sorry, I thought I'm appreciating my memory, but Padma Vihar. So I had a wonderful sight of the crescent moon in the night. And in the morning, it was even more beautiful. These are the pictures I took yesterday morning. And you see, this is since in that direction, sun is on the other side, so you see the reflection. Then there is a reflection of that building from here. So it was a wonderful sight. Then you have seen these kind of flowers. Then you see flowers. It's not a full bloom, just occasionally you see flowers. I was very impressed by this art, because there is a reunion of 1965 batch of 1965 batch of IITians. So I saw many colleagues, senior people there. So that is beautiful flowers decorating the mat there. Anyway, now since I am talking about quantum and so on, I want to tell a little bit about Perimeter Institute, which is very special. This is Mike Lazaridis, chief of BlackBerry. He was passionate about theoretical physics when he was young, but poor guy, he could only become a billionaire, not a theoretical physicist. So at some point he supported this institute with a donation of $150 million. So far he has given $400 million. It's very nice to talk to him, which I have done a couple of times. He says society has to respect theoretical physics because it has changed humanity. For example, Maxwell's equations is at the root of radio communications and electromagnetic radiations and so on. So he says society, we have to help theoretical physics and fund and so on. So not only he is giving this money, he has inspired many others in the neighborhood to donate money. And we have many people in our country now, and across the world and in our own country. And I believe that Nandan Yelankani, Inakani and many others contributing to IIT Mumbai. And then I had the opportunity to meet Mani Bhaumik 2 years ago. Again I met him last year and this year recently in ICT. I do not know how many of you know him. He is a billionaire, 93 years young man, old young man. He is passionate about theoretical physics. Even now he writes articles. So he is from IIT Kharagpur, one of the first graduates from IIT Kharagpur. He did a PhD there. He became famous because of LASIK surgery. He was inventor of this dye laser. So that made him. And so it's very important that rich people are told how to support science. And apparently they are always afraid to give money to people. But if you sensitize them, they will give money. You have to properly tell them, because we theoretical physicists we scientists are not going to run away with the money. We don't know how to do that. So it's worth spending money for science. Okay. Now, when I looked at this campus, like beautiful campus like this, part of forest or IIT Madras or many other places, I am reminded of the wish of my friend Vikram Soni. I do not know how many of you know. Some of you may know this. He is a nuclear theorist, also a condensed matter physicist. He is 75. He is at Delhi. In addition to physics, he does a lot of surveying of about fresh water and about forests and so on, ecology. So I will tell about, he says, every education institution all over India and the world should become green like and be like IIT Bombay, IIT Madras, pyramid, close to nature and alive with life. Education institutions are temples of learning. Traditionally, places of worships are housed in sacred groves. For example, in Tamil we call it a stopu, where rare species of plants are there, homes for birds and snakes and so on. So opportunities to appreciate nature's beauty and secret should be present in the campus. This is Sony's wish. If there is time, I will tell about Sony and his activity a little later at the end. Okay. Science has been undergoing an unusually long and intense revolution in the last 100 years. We can partly attribute this to our understanding of quantum secret of nature. Everybody will agree with that. And science unites. Our humanity was never so united as it is now, because we have about 8.5 billion people now. We are united. Of course, we have wars and so on, borders, but the number of wars and number of deaths are much less compared to what it was long back. Science educates. Education, propagation and sharing of knowledge is an integral part of science. Education to billions is possible now, and also with internet and all the cell phone, you can do NPTEL courses and so on. People, I was told about a boy at Chennai. He studied up to 10th grade. He was a server in some hotel. Somebody told him about NPTEL and spoken tutorial and so on, about online courses. He took it seriously, and in the evenings he studied it, continuing his job in the daytime. Now he is in Silicon Valley. After 6 years, he has no degree, he has not gone to college, but he took these courses seriously and learned it, and now he apparently well in an interview, and he is working in Silicon Valley. So things are changing. Educating to billions is possible now, science. And method of modern science is something that I don't need to talk about. And another fascinating thing, science has made humanity feel humble. We are not the center of the world. Astronomers are continuing to discover hundreds of new solar planet systems and potentially life-supporting exoplanets. I think that will be the future now. We will go to other planets and so on. There is commonness between a bacteria and a man. Universal DNA and protein machinery operates. It's amazing that when you take a mouse or a cockroach and me, the difference in amino acid is only about 5 or 6%. There is a lot of commonness. So same set of amino acids, nucleic acids and similar proteins. So modern science has shown us an organic link of ourselves with the rest of the living system. Caste, race dissolves in front of science. Okay. Now, in this background, quantum mechanics is considered as one of the greatest creative act of human mind. Because we know about literature, art and so on, and thousands of years people have been writing poems, there are sketches, sculptures and so on. But quantum mechanics is another creative act of human where collective aspect comes out, as I will discuss. And before I do that, I will talk about how quantum mechanics and science has united humanity. For example, the history of quantum mechanics is separated into two boxes. Planck came up with the hypothesis of Planck's quanta, then Einstein, Bohr and S. N. Bose. This is a classification according to Dirac. The classic papers, in 1900 to 1924. Then came de Broglie hypothesis, Schrodinger equation, or Heisenberg and so on. So collective effort, unique in human history, because never in the human history people from different continents, different races and so on collaborated in the past. Because there were people, great people, isolated, they worked among themselves. But this is a unique thing. So forerunner of the collective international character of modern science. Now if you look at modern science, it's very collective. Everyone is standing on the other shoulders of other giants who could be in Korea, or who could be in Japan, or could be in Canada, or in Timbuktu, anywhere. So it's a forerunner to the collective international character of modern science. For example, if you take ICTP, Institute for Advanced Studies, All India, many places, all over. And also, you know about Human Genome Project. Thousands of scientists all over the world work together to find out the genome of human being. Now it's more. Similarly, there is something called E8 group, supposed to be a monster group in Lie group, continuous group theory. It has number of irreducible representations, thousands. So 10 years of cooperation among 1000 mathematicians resulted in a complete classification. So imagine a human cooperation. So at the personal level, I am from Madurai. I studied in Madurai American College. R.P. Rees was he came to Madurai American College for 1 year. It turned out the American missionaries invited people to come to Madurai to teach physics to these college students. So he volunteered, came with his family, and then he fell in love with Madurai and stayed for 35 years. He started postgraduate courses, and he was a scientist at Bell Telephone Labs, working on devices and the spectroscopy, quantum physics. So it is he. One day I met him in the summer. He asked me, Baskaran, what are your plans? I told him, I had no plan actually. I told him I want to become a demonstrator in a college. He said, suppose you don't get it. Then I said, I will become a research scholar in Madurai University. Suppose you don't get it. I didn't know any answer. Then he told me, do you know about the existence of Indian subscience? I told him no. Do you read newspaper? No. And he said, for the sake of knowing a place like IASC, you should read about the newspaper and apply there for PhD program. That's how I landed up in IASC. Then I met great people like Michael Berry. In fact, Michael Berry during my PhD gave 20 lectures on not Berry phase, in fact just before the Berry phase, on nonlinear dynamics, chaos and so on. Then I met Erio Tosati, ICT, Phil Anderson, Colter Cohn, all these people, quantum people, and so at a personal level, the sciences help enormously large number of people. Okay, so life is inseparable from light, we all know. It's a picture I took a couple of years ago when we were driving from Los Angeles to San Francisco. We went to the side road and there was beautiful flowers. I took this picture. When I showed it to somebody, said that you have not seen Valley of Flowers in the Himalayas. They are even more beautiful. I want to see them sometimes. So light enlightens, literally true. Over centuries it has eliminated our path to understanding our physical universe. Efforts to understand black body radiation gave birth to quantum mechanics. That's well known. Same light and electromagnetic wave phenomena reveal the secrets of space-time through special theory of relativity. As you know, Maxwell's equation, Lorentz discovered the Lorentz symmetry, Lorentz transformation. So Maxwell's equation exemplified special theory of relativity in a fundamental way. So that's also a connection to, and also light is a visible manifestation of quantum mechanics. I wrote about it in some article. And also I remember a very beautiful talk by Professor N. Mukunda, who was my professor at IASC. He said, he introduced to us a work by Majorana, where he says, if you take Maxwell's equation and write it in vector potential note A mu, D mu and so on, it can be thought of as a Schrodinger equation for a photon quanta. But since the mass of photon quanta is 0, since it is relativistic, Planck's constant on both sides cancel each other. So in some sense, so and then A mu, the 4-component vector, is like the 4-component wave function of a photon particle. So that was Majorana's work. So in some sense, Maxwell's equation exemplified quantum physics even before quantum mechanics was born. So light in that sense is a visible manifestation of quantum mechanics. Okay, light enlightens, this is like just a, so these are Planck distribution, you all know about it. Now spectral energy density, energy per unit volume per unit frequency at a temperature T is given by the famous Planck distribution. This was the Planck wrote it using the idea of oscillators and quanta of photon coming out and so on, and this is a formula, and it was based on some ad hoc assumption. This was derived. Then later Einstein tried to improve it and various people tried it and they got the final result, but there were a lot of logical inconsistencies I will discuss later. So that's when Bose comes. Bose realized the logical inconsistency when he was teaching students at Dhaka. He was an assistant professor in a college. He was very dissatisfied with the then derivation of Bose statistics. So he introduced his hypothesis. Then that's the beginning of the history. And if you look at the black body radiation, it's amazing. Look at the distant sky at night, the end of the universe or beginning of our universe is a black body radiation at 3 Kelvin. Nothing can fit better than black body radiation. So it has been there for billions of years. So it started nearly 100 years ago, Planck's law and the hypothesis of light quanta. You can get all these things in the internet. So it is in India, as you know, whenever somebody's picture comes in the stamp or rupee note, he is a great man. So Mahatma Gandhi is there in every rupee note. Similarly, Bose is there in 1 rupee stamp. Einstein is there, and if you look at the captions here, it's nothing to do with Bose statistics, general theory of relativity, gamma, mu, and so on. Apparently, Bose was a very, very versatile guy. He studied general theory of relativity. He studied, he did X-ray crystallography. He studied minerals and so on. He was a real scientist, great interest in many things. And apparently, he and M.N. Saha, they translated Bose's original papers from Germany to English and published it. So that was very helpful when Bose sent his paper to Einstein saying that please translate it and publish it in your journal, Zeitschrift für Physik. So he said that I am interested in your work, I have already translated and so on, that helped him. So this is the abstract of that paper. I will just focus on this. This is the content of the, at the beginning of the article, Bose writes, a remarkably elegant derivation has been presented by Einstein. This author has recognized the logical deficiency of all previous derivations and attempts to deduce a formula with reference to the classical theory. Okay. But however, Bose finds a fault with even Einstein. He says, Wien's law is based on the classical theory, and the correspondence principle supposes that the quantum theory be in agreement with the classical theory in certain limits. So in all cases, it seems to me that the derivations are not justified in a sufficiently logical manner. So even though Einstein wants to overcome this logical inconsistency, he is not complete. That's what Bose says. So he politely points out Einstein's fallacy, and then he gives his own derivation. That's the beginning. And Einstein was great, and he appreciates Bose's criticism, takes it in a positive way, and then goes ahead. That's the beginning of Bose statistics. Okay, then I will. So just a digression. Importance of international programs and visitors and so on. You know that Sommerfeld apparently was invited by Raman, and he came to Calcutta. And that time he has to first get down at Madras, Chennai airport. So Chandrasekhar was an undergraduate student. So he gave a talk at Presidency College about Fermi sea, Sommerfeld theory of like Pauli principle, Fermi sea and so on. And Chandrasekhar, young Chandrasekhar, listened to it carefully, and that was the beginning of his work on Chandrasekhar's mass, that is how Pauli pressure will work again, will overcome or compensate gravitational pull in a relativistic matter. That's the beginning of black holes and Chandrasekhar. So imagine, look at somebody giving a talk in Presidency College. Before he went to Calcutta, I think he took a train and he landed there, and that's so beginning of modern astrophysics, astronomy, new telescope, and so on. So it's very important to have this kind of visits and so on, and which is happening very, very many times now, thanks to institutes like IIT Bombay and so on. So Newton's laws versus laws of quantum mechanics is something for general audience. Now many of you know this. Determinism versus uncertainty. Classical mechanics, particles, fields, Newton's equation of motion, position, velocity, trajectory, theory of all these deterministic things. And what is amazing is the predictive power of algebra, calculus, and differential equations. In fact, the strength that physics attains is from observation of experiments and trying to comprehend it, and use mathematics to rationalize it, to put it in a framework. So it's a three things: experimental observation, mathematics, and conceptualization, which go in hand in the progress of physics. So it's very important to, I tell the students, because many, at least from the place where I come from, Chennai, mathematics is given the last priority in many places, because like quantum mechanics is often called out of syllabus. Students memorize some things and try to get away with it, but I tell them you should learn mathematics very deeply, because mathematics is what gives you power to whatever science you are doing. So laws of physics are different at atomic scale. So Newton's laws, hand over to Newton's laws of quantum mechanics. Basically it says that particles behave as waves. That's a de Broglie. So when the wavelength is much larger than interparticle distance, then quantum physics comes into play. There is quantum tunneling, and linear superposition, which leads to quantum entanglement. So most quantum phenomena defies common sense and have classical intuition. This is something very it's beautifully elaborated through Schrodinger's cat paradox. So quantum phenomena like entanglement and the coherent superpositions are mathematically beautiful. You can explain many of them using 2 by 2 matrices, or a direct product of 2 by 2 matrices, Hilbert space and so on, linear vector space. But if you think about it, in our classical way of thinking, they don't make sense. That's why often Feynman says, shut up and calculate. Don't worry how quantum mechanics came. If you know the games of 2 by 2 matrices and direct product of 2 by 2, you can become a great quantum mechanic. You can get even a Nobel Prize. Don't worry about how it came about. Anyway, that's the power of quantum mechanics. So, at the beginning of quantum mechanics, Schrodinger equation, a wave equation, it says that psi is a complex probability amplitude. You take the mod square of psi, that represents the classical probability, whereas psi itself is a complex number which depends on the positions of the particle and time. Now, when you come to quantum mechanics, mathematics forms a Hilbert space formed by physical states or linear vector space, and even linear combination of them makes sense. So that's what non-classical correlations and quantum entanglement, everything. I will not go into the details of them. What is important in our context is, it was after Bose's identification of identical particles, he said that if you do counting in statistical mechanics, you have some in mind and a tag to every particle. But if there is no such tag, he has to do a very different kind of stats, which is what Bose did. He said there is something about identical particle nature which is important. Every configuration is identical, whether interchange. So what Dirac did was, he exemplified it by saying that you take the waveforms of, for example, two particles, 1 and 2, coordinate 1 and 2, you interchange it to maintain classical probability. Two things are possible. One is the wave function doesn't change sign. Another is it can change a sign. These two are the allowed things. So this defines a family of particular bosons and fermions. And once you have this has profound consequences like bosons and condensations with a finite number of particles, you have Fermi sea. See, a simple observation of Bose. In fact, that history is something fantastic, how Einstein's imagination was triggered and he went back to de Broglie's wave hypothesis and Schrodinger. It's a very complex history. I will not go into, I have no time to go into that. I can give references, please read them. So it was a fantastic insight of Bose. Now this is these two great men, S.N. Bose and Paul Dirac. Apparently Paul Dirac visited Bose when he was 75 or so, something when he was. These two great statisticians from India, S.N. Bose and this is C.R. Rao. In fact, C.R. Rao was a classical probability theorist. He retired at the age of 60 from ISI and went to Calcutta, US and got President's Medal, and he is well known for his very important work. It's something called Kramer's Rao bound, which is well known in, which is used in quantum communication theory now. Kramer's Rao bound. So that is C.R. Rao. And I have had the pleasure of listening to him once, about 10-15 years ago. He came to IIT Madras and gave a talk about joy of mathematics. It was a beautiful talk, so I have listened to him. He died at the age of 102 just last year. Amazing guy. So these are all S.N. Bose, Saha and Mahalana Bose. They are good friends and so on. Okay, so now boson Bloom. So I am a condensed matter physicist and I am also worried about materials and so on. So experimentally, we know light moves with the velocity of light very fast. Then there are bosons and in standard model of, what standard model is, it unifies weak electromagnetic and strong interaction. It is very relevant for the level of protons and electrons and quarks and so on. So there are many bosons here, photon, gluon, Z boson, W boson, and then there are condensed matter. I will come to it. Anyway, another see, I do a random walk. So you see, Salam was a great quantum scientist. I had the honor of knowing him from 1976. So what he did was he built up this ICTP, International Center for Theoretical Physics. In fact, if you want to know more about it, there are beautiful talks I have been, including my own, about Abdus Salam and ICTP, how he made the place what it was by his efforts. So in 76, January I landed there, and the first day Salam invites all the students and gives a talk saying, that I'm very happy you are here, that the idea is to put you with the best mind from the world, rest of the world, all of you are here, so please make good use of it and perform. Then he left. Then this was a long 3-month school on interaction of radiation with matter. And so we had even offices, 5-6 of us were sharing an office. And 1 week, in the second month, February or so, I kept seeing an elderly gentleman next door. I asked someone, who is that? He said, it is Paul Dirac. Then I remembered Salam's statement that it's for you to perform now. So this is Paul Dirac. This is wife. I believe this is Alfred Kastler. This is my friend Michele Parinello, Parinello algorithm and so on. And this is Paolo Budrich, who was the right hand to Professor Salam. This is also another important thing. All the friendship that you have now is going to be useful to you later. See what happened? Salam had this vision that saying that science is important for third world countries. It's very important, so it should be developed in third world countries. There should be theoretical physics. So being a theoretical physicist, so he wanted to do something about it. Salam said, Paolo Budrich said, why don't you begin it in Italy? I know the mayor of Trieste city, so I will talk to him and get you a beautiful piece of land. So he got a beautiful piece of big land near Miramare Castle, and that's how it started. So it's good to have good friends and meet them later also and as alumni and so on. So and ICTP, we have forgotten about ICTP now, because 50 years ago theoretical physics was not completely unified in India, China and so on. So ICTP was the place where it nurtured theoretical physics activity. For example, I met all my theoretical physics colleagues from India for the first time in Italy only. For example, Mukhopadhyaya, who is no more, Pragati, I met them, and I think also Ghosh, all these, Rajaraman, S.K. Joshi, all these people I met in ICTP for the first time and then later in India. So ICTP played a very important catalytic role. Okay. So there are many particles, zoo of elementary particles. So if you look at the list of so-called elementary particles, there is electron, positron, proton, neutron, they are fermion. Then you have photon, meson, pion, gluon, Z boson, W particle, Higgs boson, they are all bosons. Then when you come to condensed matter physics, there is even its richer, because as Anderson said, the more is different. So there are emergent particles. For example, you can do it in cold atoms, ion traps, or superatomic solid state and so on. So there are Goldstone modes which are also boson. Phonon is a Goldstone mode, magnon is a Goldstone mode, exciton is not trion. A trion is a fermion, unfortunately, polariton, plasma, resonance and so on. So there is fermionic electron, hole, composite fermion, even graviton analogues exist in fractional quantum models, spin 2 particle. So, and also very interestingly, in a 3-dimensional world we have only 2 kinds of, mathematically speaking, we have only 2 kinds of particles, bosons and fermions. But if your world is 2-dimensional, then there is something in between called anion, the name given by Linus Pauling, name given by Frank Wilczek. There are fantastic generalizations of the idea of Bose and so on. So many interesting things happen in this field of elementary particle physics and emergent particles. Okay. Now, as you know, Bose derived Bose statistics without any logical inconsistency, making a hypothesis of indistinguishability. He put it mathematically beautiful. I request you to read the paper. Then what Einstein did was, he said that suppose bosons are not like photons, there is a number of bosons are fixed, like by a chemical potential. We found the remarkable phenomenon of bosons in condensation. So that heralded the beginning of macroscopic quantum phenomena. Like if you go to the lab here, your colleagues here work on superconductors, quids and so on. You see macroscopic quantum coherence, order in momentum space, upper diagonal, long range order. All fantastic things, super radiance, laser, superfluidity, cold atom, Josephson effect, superconducting flux quantization. And I will talk about little bit about boson benching and so on. Even quantum. So many things happen, all from identical particle nature and macroscopic quantum coherence and sensors and all kinds of things. I will not do this right now, I will come back to it later. Now, if the quantum that began, now it has completely, become wild in the sense. Is quantum simulations, quantum algorithms, quantum annealing, quantum optimization, quantum supremacy, people fight about it, quantum decoherence, quantum error correction, there are many people in IIT Bombay working on it. And then suddenly nuclear spins are becoming very important, electron spins are important, cold atoms, neutrons, Josephson qubits, boson. And who would have suspect that in biology there are things going on amazingly at warm at room temperature. There is in bird navigation, in smell, and then various things. It's photosynthesis, quantum coherence at the warm wet biological systems are experimentally seen. We don't understand it, how it is happening. So nature seems to be much more clever than we are. So all kinds of things are happening with the quantum front. I'll come to it later. Okay, now I'll tell a little bit story and then come back to it. So during 30s and 40s, Bose became increasingly passionate about Indian independence from 200 years of British rule. When this finally occurred in 1947, he was elated but could not accept the partition of Bengal and India. In 1962, Bose went to Moscow via Sweden to attend the peace conference organized in memory of the dropping of atom bomb on Hiroshima and Nagasaki. He then visited Japan and was impressed by Japan's scientific and economic. This is part of Bose history. Now, this is a very interesting, I showed a picture already. Dirac had a great admiration for Bose. So Dirac coined the name boson to describe the family of indistinguishable particles whose many particle wave functions are symmetric under the interchange of coordinates of any two particles. So that's the name boson was given by Dirac. And apparently Dirac was surprised when he visited Bose that Bose was not a fellow of the Royal Society of London. So it was shortly after Dirac's visit that S.N. Bose and S.K. Mitra, the later well known for his pioneering research on radio and wireless, were elected belatedly in 1958 as fellows of the Royal Society. So that's the kind of respect that Dirac had for Bose, because Dirac realized that Bose's work was a turning point in the history of quantum physics. As it was Dirac who also said that in the history of quantum physics, Bose's paper is the fourth important one. Planck, Einstein, Bohr, and Bose. Okay, that's. Now, also another story, Raman and Bose lived around the same time, they were friends also. There has been a special friendship and mutual admiration between Bose and Raman. Raman Station has a beautiful article, I will give the reference at the end. In fact, I remember, I think Bose passed away in 1976 or so, when I was a postdoc at IAC. So there was a meeting, Professor Raman Station gave a talk, I think I remember hearing about. So Raman Station in an article, there quotes Bose. In fact, I was so impressed with the discovery that when we were on a walk along the Hooghly, I told him near Princeps Ghat, Professor Raman, you have made a great discovery, you will surely get a Nobel Prize for it. That was the admiration that Bose had for Raman's work. Then there is another thing. It's also, when Bose sent the article to Einstein, he had implicitly assumed that bosons are particles, they carry an intrinsic angular momentum, plus 1 or minus 1 with the right unit. He said it should be there to explain the experimental results. And Einstein apparently removed that factor of 2, saying that we are saying something more important, let's not do it right now, we will do it later. So Einstein removed it from the paper. So when that happened, is the following. In the famous paper which confirmed experimentally presence of quantized angular momentum carried by photon particles, Raman and Bhagavantam state, we understand from a personal communication by Professor Bose that he envisaged the possibility of a photon quanta possessing beside the energy h nu a linear momentum, also an intrinsic spin or angular momentum of some unit around the axis parallel. It's like this was before Pauli suggested quantized spin angular momentum of half first electron. So historically, Bose was the first to define quantized angular momentum. We say that photon is a spin 1 object. It is true, but because its mass is 0, one direction is always along the direction of the motion. So you are left with 2 degrees of freedom, which is a spin 2 angular momentum. Or classically, it's called polarization. Quantum mechanically, it's a 2 angular momentum that Bose said. So the 8 factor 2 thus arises from the possibility of the spin of the quantum being either right-handed or left-handed, corresponding to 2 alternative signs of the angular momentum. So this is again another remarkable discovery of Bose, which later came to be known through this work of, in fact, again I give the reference at the end. Now, how the bosons, from black body radiation to black hole, from the Big Bang we see the radiation that's coming out, cosmic ray, microwave background radiation, cosmic microwave background radiation. From black holes we are supposed to get Hawking radiation, that's also a boson. There are analog of that Hawking radiation in condensed matter system, that's another beautiful story. Then quantum tunneling of photonic particles, a beautiful work by Ghosh, Home, Dipankar Home and J.S. Agarwal. Dipankar Home and Dr. Ghosh are in Calcutta and Agarwal is in somewhere in the US, old friends. So lasing a cooperative phenomenon in laser, superfluidity, superconductivity, macroscopic, quantum mechanics on the tabletop. And another very important thing is, when the theory of superconductivity was developed by BCS, it was noticed by several people that the way that BCS did the theory, there was gauge invariance was missing manifestly. So this was a big complaint by people. It was Phil Anderson who said that if you do it carefully, you can do it gauge invariant way. And then what happens is the Goldstone mode becomes a plasma, a gap excitation. So Anderson suggested a mass acquired by a Goldstone mode, which is a mass generation mechanism. That's why it's called Anderson-Higgs mechanism. So Goldstone mode occurs, so it's imagine from a dirty superconductor, you get insight into origin of mass of elementary particle. That's the nature of science. Science, it doesn't care about size and shape, it's dimension. So from condensed matter, you got a beautiful insight into. That's why it's called Anderson. So when Higgs particle was discovered, I remember I was in Princeton. One day was so the whole Princeton University was very jubilant because tomorrow they are going to announce the discovery of Higgs particle. I was having tea with Anderson. He was, and everybody called it as Anderson Higgs particle. He said, please don't worry about it. Let Higgs get Nobel Prize because I have got already one. That was his point. So he was so excited that Higgs got the Higgs particle was discovered. His mind went into other questions like what is the spin of Higgs particle? Have they found it the spin to, and many other technical questions other than about Nobel Prize. And as deserving case, Higgs got it later. Okay, now I will come back to this thing. So these are something about Bose as a man. He was a remarkable gentleman. I have heard many stories about him from friends recently also. So a scientist, however great his achievement is, he is a human being. Bose's greatness is visible in the anecdote described by Ramaseshan again. So once Ramaseshan was visiting Bose, he told Bose that it was the only statement in a scientific journal that he had proposed for the first time that photon had a spin, which I described before. So I had asked him whether something should be done so that he be given the credit for proposing the existence of the spin of the photon for the first time. Bose suddenly showed some anions. You are descending from the sacred to the profane, as the saying goes. So apparently Bose said, what is important is whether the photon has a spin, and it's not important as to who proposed it first and when. The high aims of science get very debased by such talks of priority, etc. Then Ramaseshan says, I told him that I stand rebuked, but my respect for the man went up greatly. And the punishment that Bose gave to Ramaseshan was that now I have to punish you. You have to listen to my playing the Esraj. Apparently, Esraj is some kind of violin or some veena instrument. He was very good at it. So he played Esraj, and it was a delightful ending. After half an hour of Esraj, I rose and said goodbye. That's the story. That's how it goes. And apparently, Bose was very fond of Esraj and also cats. So he had plenty of cats in his office and the room. So whenever he fed the cats, because there is a scientist by name Suprana Sinha, I don't know how many of, she is a quantum person, she is at Raman Research Institute, wife of Joseph Samuel, my friend. So apparently her mother, I forget the name, was a student of Bose, doing a PhD in X-ray crystallography. She built an X-ray machine with the help of Bose and so on. So she used to go to Bose and play with with Yesraj and various cats and so on. So she told that story. And another story that she told me was very moving. There was a worker of whom Bose knows, whose daughter has to get married, so he wanted some money from Bose. So he goes to him. Bose asks somebody else, to his secretary, take the purse and give some money from there. So the boy takes that purse and gives about 10 rupees or so. He says, no, that's too small. For marriage, you give all the money that is there. That was Bose's generosity. Anyway. So Bose played Yesraj and Einstein violin. Bose statistics and Bose-Einstein phenomena continue to provide music to our ears. See, bosons have a tendency to condense, right? So there is a famous experiment called, please can somebody expand that? Mendel is the last person. Hong-O-Mendel effect. Basically, you take a prism, two prisms like this, send two beams of light, you look at what comes out. You can do a very simple mathematics. So the two photons come out. So depending on, so you send the two photons in the two arms at different time. So when they go at the same time, there is a dip. That means the two photons that come out is in the same mode. I send one photon in one mode and another photon in another mode. When they come out, they come either in those, that is this state. Two photons in mode 1 or two photons in mode 2, never at 1, 1. So you have a dip. When they are not coincidental, there is a dip, they are individually seen in the two modes, but when they are in coincidence, there is a photon bunching, it's called photon bunching, two photons come together. So the Bose-Einstein condensation has a manifestation even at the level of two photons. So this is called Hong-O-Mendel effect, and it has been recently suggested this kind of things are very powerful and useful in what is called boson sampling. It's a beautiful paper by Aronson and the complexity of, okay. So why I am showing this is, so again I will be very brief. So there is a way of doing quantum computation, at least for some specific task. So you have n ports. Each port is sent an n photon state. It could be, n can be any integer, 1 or 2, 3 or 4. And then there are linear optics arrays like beam splitters and no nonlinear effect. At the output, you have another n ports. So there is some probability, some photons will come. So if you want to calculate that probability as a function of various number of photons, it's supposed to be what is called a permanent, as opposed to determinant. Determinant is something that we know how to calculate. You take a matrix and then look at the expansion and then put signs and so on. In permanent, you have to, all the terms are the same sign. So it's in some sense simpler, but apparently it's very difficult to evaluate. This using boson sampling, you can evaluate it very effectively. This was done by Jian Wei Pan at China. They have about 50 to 70 ports. They say that it has some quantum advantage and quantum supremacy and so on. There are debates about it, but what is important is the boson that we talk about has really helped in bringing this thing. Okay. So this article that I wrote with Alex May is available in you can do Google search, Google Scholar, and you will get it. So the edifice of modern quantum theory, many body quantum theory, quantum information, quantum built in this boson. So I give this is a summary of that paper. Then there are fantastic review articles, earlier articles there is a book by Chatterjee on man and his work, and also another book by Kameshwar Wali, an old friend, on S.N. Bose. And then Chanchal Majumdar had some articles on, Sudarshan has an article, and Partho Ghosh, Mukunda. And also there is a recent movie which is there in this site called Dear Master, a film by Subha Das Malik. So it's worth seeing. So this is the references. Then it turned out, it's interesting that IIT Madras has a guest house called Bose-Einstein guest house. So when 4 IITs or 5 IITs started, apparently there were some countries which nurtured the beginning of it, like IIT Kanpur, USA, I think IIT Mumbai, Russia, and IIT Madras was called Germans. So the then director Anand, he knew about this Bose-Einstein connection, so he named the guest house as Bose-Einstein guest house because of the German-Indian connection. So I wrote an article about it. So that's the thing. Then I promised. Okay. So science and technology has made humanity big. Never in the history of Earth it supported so many human beings. 145 crores in India and about 820 crores in the whole world. We are a big family of humanity, all forms of life on our great earth, green earth. I hope that science and technology will help make this big family into a happy and blooming family. Sorry, the family is missing because of the ladder. But thank you very much. But let me, so shall I stop here or? Okay, then I will tell about my friend. See, I wanted to mention this because we are in a very special campus like IIT Madras, the wilderness, and there is beautiful nature coexisting. So Vikram Soni was my colleague at Department of Theoretical Physics. He is retired as a UGC professor. So he, in addition to theoretical physics, he Soni builds bridges between science, communication, nature, wisdom, and so on. I will not. So we have written papers on quantum condensed matter also. What is interesting about Vikram is that he has started a foundation called PISCI Foundation, Public Interest Science, that's a website. So it had distinguished key founders like M.S. Swaminathan, who is no more, Tony Leggett, a Nobel laureate from Urbana-Champaign, Rajendra Singh, waterman of India, and Arvind Nirmani, among others. So what they do is, Soni does wonderful things. When I saw IIT campus, and I was reminded, so Soni and the Romy Khosla, a famous architect, internationally well-known, they came up with a proposal for Amaravati when the city, about 10 years ago, when the city was about to be built. So their point is, it should coexist with nature. So this book can be freely downloaded, and so you can see at least the imagination how it was. Then, being a physicist, they have a scale-free landscape. So how, as you go to deeper length scale, still there is forest and so on. So this is, when I see IIT Mumbai and IIT Madras, I am reminded of that other campuses. He also has a beautiful book called Naturally. It's a very well. So Tony Leggett writes, Vikram Soni has for many years been a leader in the fight against the intersection of nature in his home country, India, and elsewhere through his planet. The book he describes and so on. Okay. Yeah, I think I will stop here and answer any questions if you have. You can see how enchanted I am by the campus. Fantastic campus. I wish every campus is like that. I wish it's fun.
Okay, we can. Thank you for the general talk now.
Good evening, sir. Sir, I had a journal or rather a personal question. Sir, can you suggest me a way to transition from engineering to theoretical physics? Because that is what I want to do.
That's the question.
Yeah.
Do you know Dirac was a chemical engineer, electrical engineer, and Landau was a chemical engineer.
Oh.
So you have four fathers now who have shown the way. So it's very simple. Just read theoretical physics,
yes,
or use your engineering mind to theoretical. There are many problems open to. So transition is, in fact, I have a colleague by name V. Balakrishnan, who has inspired many engineers into become theoretical physics, including our marathon runner, but Suresh Govindarajan, who was a mechanical engineer, became a string theorist. So many people are there. So you can listen to his talks online. And also talk to colleagues here, there are many engineers and Umar Shankar, yeah.
Yes.
So, in fact, the training as an electrical engineer is very helpful apparently to do. Okay, and also since if you are, for example, do you know Umesh Vazirani? He is a well-known name in quantum information and so on. He was an electrical engineer. So he has a course on quantum information theory, where he says you don't need anything beyond 2 by 2 matrices. which electrical engineers know very well.
Yes.
Similarly, the prime number factor is about this Peter Shaw. He was also an electrical engineer. He did wonderful work in quantum information. So they have shown the way. So since you have good understanding of mathematics, you can get into at least quantum physics very easily. There are many opportunities.
Yes, sir.
I wish you all the best.
Thank you, sir. So thank you, sir. Such a beautiful lecture. My question is, can you talk a little about that quantum biology part? What you were saying, bird navigation, photosynthesis.
Okay. So let me start with bird navigation. This is a beautiful work by Klaus Schluten. So he observed that birds, for example, fly from the north of Africa to South America over 2000 miles above the sea in the dark night. There is no guidance from sunlight and so on. So the only directional thing is Earth's magnetic field. The Earth's magnetic field in units of temperature will be 1 Kelvin, G mu will be 1 Kelvin. We are at 300 Kelvin room temperature. So Boltzmann factor will kill everything. But still, how birds are able to fly? So he came up with a hypothesis. He said these were a hypothesis plays very important role. I do not know what's going on, but there is some species of intermediate in the metabolic pathway. There is some intermediate species of molecule wherein there are two electrons well separated in space. They are weakly coupled. So they form a ground state singlet and triplet excited state separated by 1 Gauss roughly, G mu b. So the splitting, singlet triplet splitting is about 1 Kelvin. But thermal fluctuations will make it equally populated. But however, he said there are nuclear spins which are very weakly coupled to the electron spin through hyperfine coupling. They are decoupled from the environment. They have coherence times of minutes and hours. So he said somehow that dictates the direction. So with the hypothesis, it was confirmed experimentally. So nuclear spins, since they are a subsystem which is very weakly coupled to the environment, you cannot define temperature to them easily. Like in fact, if you go to Kittel's book, you will find nuclear spin temperature versus lattice temperature. They can be very different. So that's one thing. Then in olfaction theory and also in photosynthesis, photosynthesis is a fantastic phenomena in which there are, if you take any photosynthetic system including bacteria, there is something called chromophores which absorbs light and creates an excited state called exciton, and they run around in some circular disk. Experimentally, if you do a simple theory, you will find that they will hop rather than coherently run around. But to their great surprise, when they did experiment, they found they coherently run around at the warm wet temperature. Even now, we don't understand it very well. There are some explanations for them. And also, they have profound consequences. When many particles are together, there are some coherence effects coming from fermionic condensation. I have written a paper about it. So, I have made a statement somewhere in one of my articles saying that we have discovered, human beings have discovered quantum mechanics the last 100 years under special conditions, special materials, special laboratories and so on. Whereas nature has been doing experiments for the last 3 billion years. So they know how to use quantum mechanics more than we do. So there will be surprises. So I also wrote another place saying that whatever we have learned in condensed matter physics or quantum matter physics in the last 1 century is a warm-up exercise to do, climb our Mount Everest, which is understanding biology. Anyway, I can tell you more about it later.
Questions? No. Okay, so with this I will give you a memento and thank you for...
Sorry for boring you, with some stories and so on. It's a very incoherent talk, but random walk, but that's a way.
No. So actually it was very inspiring. There are many things that I did not know about in the historical front, and as well as just now that some of the answers that you gave. So I think we can take with us a great inspiring message after this talk, especially the unification of, science doesn't see borders, and in this world this is very important at this moment. Okay, so with this I will give a small token of appreciation from IIT Bombay. Yes.
Thank you.
Okay, so if you don't have any questions, we can adjourn the Colloquium. Thank you.